Okay, so thanks for joining us. Today we have Michał Włodarczyk from Eindhoven talking about his recent papers about Steiner orientation.
Hello, thank you for having me. So I will maybe start with some small historical introduction why I ended up working with this problem. So Steiner orientation was, it used to be an open question whether this is FPT or not in my early PhD years. And Marek Cygan and Martin Pilipczuk tried to resolve this problem. And later, I also tried to show that this is FPT, and I failed, but probably because not much time later, Marcin and Magnus Wallström showed that this is W1 hard. And I was a bit sad because of that, but not only because they proved that I'm wrong, but mostly because they used some, they proved W1 hardness of both Steiner orientation and directed multicut in their paper, and they used one gadgeting machinery. And I thought that Steiner orientation has some nicer special structure, which makes it different from problems like directed multicut. And then I revisited this problem a few years later from the point of view of FPT approximation, and it turns out that in fact, yes, it has some like a special structure on which I will be talking today. So I will begin with an introduction to hardness of approximation business and introduce some main ideas and techniques. Later, I will talk about the problem in question. What is it about? What is known? Then I will show how you can nicely make some gadgets with this problem to make some nice self-reductions. And in the very end, I will talk what are the implications of that. So this is maybe a bit non-standard schedule for a talk, but I hope this will provide like a nice narration flow. So let's start with hardness of approximation. So in this paradigm, we want to show that we have some favorite problem. We know that it admits some alpha approximation for some coefficient alpha, and we want to prove that we cannot improve upon this alpha within some complexity class. And these classes can be like polynomial time algorithms, FPT algorithms, or running time of the form n to the small o of k. And we need to choose some hardness assumption to rely on. And for polynomial time hardness, the straightforward choice is to start from p unequals np. And for parameterized hardness, to start with FPT unequals W1. But sometimes these conjectures are quite like difficult to work with approximation problems. So there are some stronger conjectures like Unigame's conjecture or gap exponential time hypothesis, which I use to this end. So in this talk, I will focus on FPT running time and hardness assumption that FPT unequals W1. And how to tackle the quest of proving hardness of approximation. So usually when we prove hardness of some problem starting from say p unequals np, we prove hardness of decision problems, not optimization task. So we need to turn the approximation task into a decision problem. And to do so, we consider gap problems. So let us focus on maximization problems. And suppose we want to show that we cannot improve upon alpha approximation. So we consider a problem with such promise that we are given either instances with opt at least k, or opt at most k divided by alpha. And we are promised that the input belongs to either of these types. And you can see that if we had an alpha minus epsilon approximation, then we could use this algorithm to distinguish between these two cases. So hardness of a gap problem implies hardness of approximation. And in the hardness of approximation, we actually prove hardness of gap problems. And we need a framework for making reductions between gap problem that would preserve these gaps. So in each gap problem, we can say that we have two languages, L1 and L2, which consist of the instances with high optimum and low optimum. And in a polynomial time regime, we want such a reduction to work in polynomial time, and also to produce a new instance of potentially different problem and potentially different gap, also of polynomial size. So the gap can vary in this reduction. So this is say alpha 1 and alpha 2, and I will use this kind of arrow to indicate how large is this gap. So this reduction should map the instances from language L1 here to language L1 there, and the same for L2. So if we can distinguish language L1 and L2 in the right, then we can also use this reduction to distinguish this on the left. So when we begin with a problem which is hard on the left and make this kind of reduction, then it also implies the problem on the right is hard. But how to find some gap problem to begin with? So finding hard gap problems is not so trivial, and sometimes you want to just assume hardness of some basic gap problem and start our reductions from there. And this is why we sometimes start from Union-Games conjecture, which already assumes this kind of hardness. But there is some other way. There is some technique to create gaps. So consider a self-reduction for some particular problem that works in such a way that first we have languages L1 and L2, where in L1 we say we can the fraction of the how large is the opt to some upper bound is 1, so we can satisfy all the constraints or something like that. And in the language L2, we know that the maximal fraction of satisfiable constraints is 1 minus epsilon. And this reduction grows this gap a little, so epsilon turns to epsilon, and the size of the instance grows proportionally. So if we had such a reduction, then we can imagine pipelining it many times and growing this gap further and further, and this is still a proper gap preserving reduction. So now the trick is that we can perform this pipelining super constant many times. So, and we can start with the initial gap being subconstant. So this epsilon, which is there, can be something as small as 1 over n, where n is the size of the instance. So in fact, we have a classical decision problem with no gap on the left if this problem is unweighted. And after iterating this reduction log n times, we obtain our last instance, which is still of polynomial size, but now the gap from 1 over n becomes something constant. And this actually is what has been proven for max CSP. And this gives alternative proof of the PCP theorem, which is like a bridge between P versus NP and hardness of gap problems. So let us take a look what would happen if we tried to make such a trick with the independent set problem. Oh, by the way, I didn't say that, but if something is unclear, then feel free to interrupt me during the talk. So for the independent set, we can consider self-reduction, in which we increase the gap in such a way. We take like a square of a graph. So the new vertices are pairs of vertices, and we put an edge between pairs whenever there was an edge in the original graph between either like a U1, U2 or V1, V2. So this construction squares the size of the graph and also squares the size of the independent set. So this can grow our gap from some alpha to alpha square. But what would happen if we tried to do this gap amplification idea with independent set? We wanted to start with a trivial gap. So just the problem of distinguishing between having independent set of size k and at most k minus 1. So the gap is here. And if we wanted to turn this gap into a constant one, then we would need to take the kth power of the graph. And we can see that the graph, the gap would indeed grow to a constant one, but the size of the created instance would be like n to the k, which is not polynomial, and this kind of reduction would be meaningless if the produced instance is too large. And for the independent set, we can do something slightly different. Namely, we can start with a hardness of a gap version of max 3 sat with some small gap, which follows from PCP theorem. And there is a reduction that from max 3 sat to independent set, which also allows us to get a hardness for some like small gap. And then we can use this reduction only constant number of times in order to grow this gap from small constant to a large constant. Okay, so let us now move on to FPT realm. So when we want to prove hardness of approximation in FPT time, we consider the analogous parameterized gap preserving reductions. So first of all, this reduction should still map language L1 to L1 and L2 to L2. And it should also be a parameterized reduction. So the size of the parameter in the new instance should be a function of the initial parameter, and the size of the new instance should be some function of the parameter times polynomial of the input size. And we'll consider problems where the size of the optimum is also the parameter. So now, if we can distinguish L1 from L2 in the problem on the right, then we could also make this distinction like on the left. So again, the hardness from the problem on the left implies the hardness at the problem on the right. And again, there is this like a problem how to start, how to begin with some gap problem which is unlikely to admit FPT algorithm. So the most common technique, the most common idea is to start with a conjecture called the gap exponential time hypothesis, which states that max tree-sat with some small constant gap admits no sub-exponential algorithm. And this is a stronger version of exponential time hypothesis, which just states that tree-sat doesn't admit sub-exponential algorithm. And starting from gap version of max tree-sat, we can make such a reduction to clique and label cover and other problems. But we need to assume this quite a strong conjecture. So what would happen if we tried to revisit this idea of gap amplification from the PCP theorem in FPT world? So we can consider again like a self-reduction in which is parameterized reduction, but the size of the instance grows proportionally with to n, as in the previous slide on gap amplification. And in each step, we can grow this gap to be this like a maximal fraction of satisfiable constraints to be slightly less and less. So we can again pipeline this reduction many times. And now a really nice thing is that as long as the number of this iteration is some function of the parameter, then this expression that we have over there is still some function of a parameter. So if t is some function of k, then we always get a gap-preserving parameterized reduction. And if we had a FPT algorithm that could distinguish from having large solution here and small solution, this would also like imply that we can solve the problem on the very left. And again, we can try to start with a trivial gap. So just distinguishing from having solution of size k and at most k minus 1. And if we can guarantee that this alpha, this gap, grows to infinity, then for like any constant, we can find some like a t which is like a function of k, which gives us sufficient number of iterations. So such a scheme allows us to rule out any constant factor FPT approximation as long as the initial problem is W1 hard. And also this this can allow us to rule out a super constant approximation, but this is a bit more tricky, because if we wanted to rule out logarithmic approximation, to say that like here on the very end, if we had a logarithmic approximation, then we could solve the problem on the left. Then observe that like a new parameter is this. It's like a k of t, which can be like a very large. And now we need to check how large is logarithm of this new parameter. So the rule of thumb is like the slower the parameter grows and the faster the gap grows, the better lower bound we can get. Okay, so this was introduction about hardness of approximation, and let me finally define the Steiner orientation problem. So here we are given a mixed graph G, so it can have both undirected and directed edges like there, and we are given k terminal pairs as ITI, and the number of these pairs is the parameter. And the task is to find the orientation of the undirected edges to maximize the number of pairs with a path from source to the sink. So we can imagine like such an orientation of these undirected edges in the left. And right now we can see that for each of these three pairs, there is a path from source to the sink, and note that these paths might like intersect. Yeah, like many paths might use the same edge. And observe that like this instance on the left, in which all the edges were initially undirected, this is like a fully satisfiable. But if we started with the instance on the right, where these like two middle edges are initially oriented to like a point up, then this instance on the right doesn't admit such an orientation. And the best what we can do is to satisfy any pair of requests, but not all of them. So what is known about this problem? It is way easier when the graph is undirected. So we don't have any pre-oriented edges. Like the decision problem whether all requests are satisfiable is polynomial time solvable. So the maximization version is FPT. In general case, the problem belongs to class XP. And as I already mentioned, it is known to be W1 hard. It is also known that there is some epsilon that we cannot 1 plus epsilon approximate this problem in FPT time and even such a running time, assuming gap exponential time hypothesis. And also there is like some other epsilon known that 1 plus epsilon approximation is in polynomial time would imply P equal NP. So we know that it doesn't admit pitas in any of these regimes. But already the question whether it has a constant approximation or like any non-trivial approximation was open. So now I want to play some like combinatorics with this problem.
Sorry, excuse me. Can I just make sure? So the K is the number of pairs,
yeah.
Right? Yes.
Okay, so I will picture an instance of Steiner orientation with such a blue box. And I will always draw the sources in the bottom and the sinks at the top. And I will represent like an orientation with such a scheme, so that these pairs which are marked like in gray, they are satisfied. So there are some paths connecting them, and this pair in white, it doesn't admit a path over there. So I will start with some thought experiment in which we take k copies of an instance. The k is 4 in this example. We put them in one row, make another copy which is like a top of them, and choose some like k tuple according to which we make these connections. So like this tuple governs like which sink would be connected to the first source in here, and so on. And imagine also that for such an instance, we also make k request. So we first like source is here and first sink is there, and so on. So you might think that such a construction doesn't make like a lot of sense, but it will later. So in order to satisfy such request, we have like two obstacles. We need to orient the edges like in the bottom layer and in the upper layer. So first, consider that we have fixed the orientation of the edges in the bottom layer, and that our instance is not fully satisfiable. So no matter how we orient the edges in each of this instance, there will always be some like a white sink which is not connected from the source. And we can encode this configuration. I will call this like configuration. This like a tuple of white sinks. So these are like sinks that are like already like separated from their sources on the bottom layer. So they like cannot be extended anymore.
I'm sorry, can I have a question?
Yeah.
In this instance that you just created, what exactly pairs of of requests do you have?
Like there, like according to this edges from the tuple R.
Okay, so on this picture there are only 4 requests.
Yeah.
Okay, good.
So now we can ask a following question. Suppose we fix the orientation in the bottom layer, so we fix the configuration tuple C. And now we'll consider like a random experiment of like choosing these like connections are like at random, and we will see like what happens. First, we'll consider a random variable y, which says like what is the fraction of these edges that are like connecting us to gray sinks. So these are the like paths that like can be extended further, because if we were unlucky and chose like R2 to hit in the white sink over there, then we know that the game is over for this request. Yeah, we like already blocked it on the first layer. So the YC is the like a random variable which says like how many paths like are still like extendable divided by k. So this is between 0 and 1. And x of c is a random variable saying that okay, like I made this connection, I fixed the orientation in the bottom, And now I'm going to find some orientation in the top instance and how many of these 4 requests I can finally satisfy, divided by k. So this is again a fraction. So in this example, we can see that y of c is 3/4 because in 3 cases we've hit it like a right sinks and once we hit it a wrong sink. And of course yc upper bounds x of c, because if we already like blocked some path in the bottom layer, then we have no hope of extending that. And the expected value of yc is k minus 1 over k, simply by the linearity of expectations. Yeah, because in each of these boxes we have this like a chance of hitting the right sink. All right, nothing fancy happening so far, but right now observe that xc is always, if we are given a no instance that we cannot satisfy all the terminal pairs, the xc is bounded by k minus 1 over k, because this is the bottleneck. Yeah, we cannot satisfy everybody in here. But if we are lucky, the yc can be as large as 1, like in the example right now. Like in this configuration, we have hit only the satisfied sinks. So this means that we not only have this like upper bound, but with a positive probability, the xc will be significantly less than yc. This is the probability that we are lucky, that we have always chosen a gray sink. So from this estimation, we can infer that the expected value of xc, so the like a total the optimal like a fraction of satisfied terminals in this like a toy instance, is strictly less than k minus 1 over k. And k minus 1 over k is was the trivial gap. So we are like starting to have something strictly less. Okay, but this was only like a thought experiment, that first we like fix the orientation in the bottom layer. So this was not a proper reduction. Let us make a proper reduction out of that. So consider putting k copies of the instance in the bottom layer. And right now we consider all the possible tuples R. So like all the possible ways of making these k connections. There are k to k such tuples, but we are making a parameterized reduction, so we can totally afford putting all of them here, and we put all of them in the second layer. So we can think of like having like a union of all the instances that we created in the previous slide. And for each GR, we make this k terminal pairs according to the tuple R, exactly as in the previous slide, and we take a union of all of this requests. So in total, we have this many terminal pairs. This is our new parameter. Okay, so what would happen if this initial instance was not fully satisfiable? Then consider any orientation of the bottom layer, and since we have all the possible tuples R in the top layer, then the behavior of the like an average of like terminals like satisfied in like each Ri is exactly the same as if we chose R at random, because we have just put the whole probabilistic space in the top layer. So the same calculations as in the previous slide apply here. So if the opt in the original instance is at most k minus 1, so like I wrote it in this way to emphasize that this is the gap, then the maximal like fraction of satisfiable terminals in the new instance will be slightly like less. And of course, if we started from a yes instance, that so like we could make like such an orientation to connect all the terminal pairs, then we could like use this orientation in each blue box, and the instance would be fully satisfiable. So we have completeness and soundness of this reduction. Okay, so it doesn't give us much yet, because we have amplified the gap by something like a very small, depending on k, but we are going to iterate this process. So we construct a sequence of instances hi, where our initial instance is like g is h0, and in each step we make the same trick. We take k copies of the instance hi. We consider all the possible ways of connecting the sinks of hi to a new copy of g, and take all this like possibilities and put in a new row. So right now the number of the tuples R is the previous parameter ki, so the number of sinks over there to the power of k, yeah, because we have k choices. So the new parameter would be this big, and the same calculations as before allow us to say that if the maximal satisfiable fraction in the previous instance was some like a qi between 0 and 1, then the new maximal satisfiable fraction is slightly less. And this epsilon k, this is exactly the same additive change in each step, because it doesn't depend on the parameter, it only depends on this like probabilistic calculation. So this is the same in each iteration.
So excuse me. So in these RIs, let's say, so the graphs are all the same, and only the requests are different, right?
Yeah.
Yes.
So in whole like reduction, we take some huge function of k, many copies of the original instance, and just like consider this like a net of different connections between them. Yeah, so if this qi is the maximal fraction of satisfiable terminal pairs, then we can see that if we started from a no instance, that this fraction goes down by some constant like additive change in each step, so we can make it as small as possible. So let's go back to this like a schema of gap amplification, and let's see that this is exactly what we wanted. Like a single step of the reduction is a parameterized reduction, and the instance size grow proportionally to n. We just take f of k copies of the original instance, and the gap is slightly growing. So this like a fraction qt, the maximal fraction of satisfiable terminals, is like a 1 over the gap. yeah, in this scheme. And this is the parameterized gap preserving reduction, because like we stop this sequence of reductions when we reach qt sufficiently small, and this number of steps is a function of k. So if we can like make a distinction over there for this large gap, then we can also make a distinction in the problem on the very left, and this was the problem with a trivial gap. This was a gap k over k minus 1 coming from the original decision problem. So this construction allows us to rule out any constant factor FPT approximation for Steiner orientation, because the original decision problem is W1 hard. And as I advertised before,
so in this you need to assume you need to start with W1 hardness of the problem. Are all of them satisfiable?
Yes. Yes, that's right. So yeah, what about we wanted to rule out super constant approximation? So as I said, like we need to keep track how fast this parameter is growing in order to keep track of the the dependency of the approximation factor and the parameter. So far we were a bit like wasteful with this parameter growth, because like recall the parameter in each step was growing according to the number of the tuples R, so quite rapidly. And it turns out that we can make it in a slightly smarter way. So let's go back to the first step of this self-reduction. But instead of taking the whole probabilistic space, so all the k to k tuples R, let's say that we just sample some quantity of tuples, and we make a randomized reduction. And this quantity m will be estimated in a second. So this is a very similar reduction to the first one, but instead of taking all k to k tuples R, we sample uniformly m of them and make such a reduction according to the same rules as before. And now some fancy probabilistics comes in. So I'm going to show that you need just small number of this m doesn't need to be too large to ensure the same properties. So recall this random variable xc, which for given configuration says what's the maximal fraction of terminals satisfied when we attach like a single gr according to a tuple R. And for our family calligraphic R, xc of R is like the average over the tuples in this random family. So this is the as the expected value of x gave an upper bound on how many terminals we can satisfy in the previous construction. So right now this is going to be the analogous upper bound. So since we sampled this family randomly, independently from each other, we can take advantage of Chernow bound and argue that this average over the random family R is not so far from the expected value of the variable x. And this is just an application of the Chernow bound, that this probability of being off the expected value, it decreases exponentially with the number of trials, with the size of our family calligraphic R. So since we want to keep this additive change of epsilon k, we set delta to be less than epsilon k, and we take these many samples in our random reduction. So if we put k log k here in the Chernow bound, then we obtain the upper bound of sampling like a wrong family R this small. And now the final trick. So how many possible configurations we have? So how many types of the orientation in the bottom layer do we have? So in how many ways we can choose the white sinks that are blocked? This is k to k, because for each copy in the bottom layer, we choose one sink. So observe that this is when we take a sum over all the configurations of this probability, then by the union bound, we get that the probability that we are off for any configuration is at most 1/2 by union bound. So we get this inequality with high probability for all configurations simultaneously. So no matter how we orient the edges in the bottom layer, our random choice of calligraphic R is good. So instead of taking k to k sized reduction, we can improve this. So let me summarize what is the implication of this reduction. Is that when we are given an instance of Steiner orientation and some parameter q, we can make a new instance with a parameter being this big. And if the original instance was fully satisfiable, then the new one is as well. But if the original instance was not fully satisfiable, then the the maximum number of terminals satisfied here is as low. So we introduce a gap of q for any q. And when you try to adjust a q as a function of parameter and see what happens there, you can see that when you take when you consider approximation factor, which is sublogarithmic, then the whole construction still works. So the gap problem of Steiner orientation with gap being so large is W1 hard. So if we could approximate this problem with this ratio, then FPT would equal W1. But there is another maybe surprising corollary, that if you consider not FPT algorithms, but purely polynomial time algorithms, then you can improve this upper bound to be like a log n to small o of 1, not log k, because you can use this lemma in a slightly different way by treating the parameter k as some very slowly increasing function of n. And you can also get a totally new lower bound for polynomial type algorithms with the hardness assumption from parameterized complexity, which is a bit uncommon. And one remark, that this construction was randomized in this moment when I talked about Chernow bound. And in parameterized reduction, we can de-randomize this because everything is a function of k. So like we can always just find on the side a family of tuples, which is fine. But in the polynomial time reduction, we cannot really afford this. So the reduction is then randomized. And in the second result, we need to assume that W1, the class W1 doesn't admit randomized FPT algorithms. And there are some other results in this paper. So this technique can be also applied to some version of max-directed multicut to also get some kind of parameterized inapproximability. And the last result is the proof that the problem is actually W1 complete. Because what Martin and Magnus showed is that the problem is W1 hard, but it was open like whether it is maybe W2 hard. So like we also establish by a reduction from Steiner orientation to k-clique that this is W1 complete. And there are some some obvious open problems related to that. So we know that the we cannot get a sublogarithmic approximation for Steiner orientation, but actually we don't know any non-trivial approximation. So like, can we raise the inapproximability bar like higher, or can we do something non-trivial? And the second question is, what if the graph is planar? Because this hardness result for parameterized inapproximability under gap ETH, which I mentioned before, this also works for planar graphs. So also on planar graphs, we cannot have a parameterized pitas for this problem. But we don't know, maybe there is a 100 approximation for planar graphs. We cannot rule it out. And the last question is that, okay, we saw this self-reduction and gap amplification for the Steiner orientation, but this was really using the combinatorics of this particular problem. And we saw in the example with the independent set, like it's hard to make some such generic reductions without blowing the size of the instance too large. So in particular for k-clique, the parameterized inapproximability results rely on gap ETH. And it is, I guess, important open problem to replace this assumption with just FPT unequals W1, but we don't know how to make such a gap amplification for k-clique. And that's all, folks. Thank you for listening.
Thanks a lot for a great talk. Maybe 3, 2, 1, we clap. So like unmute yourselves and clap. So 3, 2, 1.
Thank you. Thank you.
Thanks. So are there questions in the room?
Maybe I just wanted to say that this is actually very cool.
I agree. I agree. Can you actually say what paper was it? Because I don't think that you mentioned.
You mean like the title of the paper?
Yeah, title of the paper and where was it published? Maybe I missed it at some point.
So this is the title of the paper.
Okay.
And it was last ICALP.
Okay, good. And I had a quick question. So even in the unparameterized version, is there any non-trivial approximation like log n approximation or something like that?
There are few approximation results, but when the graph is undirected.
I see.
So the problem whether we can satisfy all the terminal pairs is polytime solvable, but if you want to distinguish whether you can satisfy like a half of the terminal pairs or like a slightly less, then it's NP-hard. There is a reduction from max cut. And there are approximations like a log n over log n, I guess, like this kind.
Okay, so still pretty bad, but yeah.
And for planar graphs, when you allow directed edges, what's the best known approximation?
There is no known approximation. Like there is this inapproximability result, but this is like a corollary from like
and it's only no pitas, no parameterized pitas.
Yeah, this is like a corollary of like this reduction. So like they managed to not only like prove like this time lower bound, but also like they managed to produce a planar instance and also to preserve the approximation ratio up to some small constant. But from the like a positive side, there's nothing found.
Yeah, that's pretty cool.
Yeah,
I didn't know that this is open. Good. No. Okay, are there any more questions? If not, then thanks again. I'm